We start today chapter 4 and chapter 5, and to give you some idea how this lecture is organized, we should start from elementary particles. That we reduce to electrons, protons, and neutrons. And by defining the interaction between these three types of particles, we defined atoms. And then by defining the interaction of atoms, we defined molecules. And now we do next step. We define the interaction between molecules, and we will discuss gases, liquids, and solids. These three are called the three states of matter. But as you probably know, there are more than three states of matter. What are another states of matter except of gases, liquids, and solids? Plasma, good. Have anybody seen plasma? Good, good. So where is it in this room? Ah, you mean this one? Yeah. But we have white plasma here. This is low temperature plasma. So what is plasma? Well, generally, if you make from atoms cations plus anions, you get a mixture, you get kind of ionic species. But you can make from atoms another thing. You can produce from atoms cations plus electrons. And this type of mixture of cations and electrons is called plasma. So this is the low temperature plasma, because probably from every atom only one electron is detached, and the rest is just +1 cations, maybe +2. But if you imagine very hot temperature plasma, then all electrons are gone. The nucleus is by itself, and all the electrons are like in metal, you may think, flowing around, making a soup. So plasma is such hot soup. So we know that there would be plus plasma. What else? What are other states of matter? You are very quiet today. Unusual. Okay. I know it's not easy, but another one would be, for example, the inside of the neutron stars. So we have a lot of neutrons glued together making one huge object, extremely heavy, 1 square centimeter. I don't know exactly, but there will be billions of tons of this neutron star. So only odd neutrons, nothing else there. Or maybe some small amounts. What is another state of matter? Think large. Liquid crystal. Yes, okay, that would be good too. So in this sense, my screen of my computer would be a liquid crystal. Coming back to the plasma, I don't have plasma screen, that's why I said no, but if I would have plasma screen, it means I would have very small bulbs like that with gas inside that by electric field can get ionized to electrons and cations and glow. So there would be also correct definition of plasma. Liquid crystals is something between liquids and something between solids. And we will discuss it later, maybe in 2 weeks. Good. Well, some people also consider black holes to be state of matter. We don't know how it looks like inside. But definitely inside a black hole there is a lot of mass inside, but we don't know what are the interactions really. Difficult to say. Good. Why most of the times people are saying that there are only 3 states of matter? Because these are the most popular on Earth. If we are living on neutron star, there will be only 1 state of matter popular one. But we don't. Okay. So we more or less discussed these things. Now we are going to discuss gases, liquids, and solid. In chapter 4, we are going to discuss gases. And in chapter 5, there will be a discussion of liquids and solids. You probably already know a lot about gases, liquids, and solids, but I hope to show you something from different angle. Good. To understand things, we should start from a picture. And the question is, this particle is outside of liquid or solid, difficult to say. Let's say it's liquid. It's in the gas phase. Now, what are the forces acting on this particle? Gravity, good. But gravity is very small. Tiny, tiny, tiny. What else? Yes, van der Waals forces. And you know the van der Waals forces change very much with distance. Gravity is more general. It acts on any distance. But with the van der Waals, when this atom is kind of close to the rest, is repulsed or attract? Okay, who is for attract? Hand up. Who is for repulse? Hands down. Everybody, hands up or down. What I'm asking is, if you put a vector of force on this particle, the vector is there or the vector is there? It's attracted or it's repulsed? So you say the vector is here, right? Who says vector is up? 1, 2. Who says vector? 3. Good. Who says vector is down? 1, 2, 3, 4, 5, 6, 7. And Olesha? What Olesha says? Okay. Good. So to understand this, we should understand that if every blue dot represents a closed shell molecule. If we have 2 closed shell molecules, and we plot the energy of 2 closed shell molecules, when that would be the energy of the two separated closed molecules at the infinite distance, we know that the plot looks more or less like that. It means there is a distance when the forces are repulsive. And if you go above this distance, the forces are always, just my plot is not very good, always attractive. Always under the white line. Tiny, very small. But what it means is that when the molecule is here, there is a small, tiny force acting in this direction. When the molecule coming close, the force first is getting larger. So when the molecule will be here, there will be larger force acting it. And finally, when the molecule come close like that, this is the equilibrium distance. Okay? Now, but sometimes there is crowd here, so everybody is pushing everybody. So sometimes two particles can get too close to each other, and then we come in this region. And that's why from time to time, when this particle at the same time is approached by 1, 2, and 3, it gets very large force this direction and goes away. That's a boiling process, right? Of the liquid, or it's an evaporation process of a solid. So you should remember that the interaction for a single particle with the bulk, this large amount of molecules is called bulk. So single particle interaction with the bulk looks more or less like that. It's slightly, very slightly attractive, and then when it gets too close, it's very strongly repulsive. Good, but this plot doesn't answer to us why some particles, some molecules make gases, some of them make liquids, and some of them make solids. Any idea? Say once again. Bonding energy. Van der Waals bonding energy. Right, that's true. This van der Waals energy can have different first different distance and then different height of the well. Depending on the molecule, you get different thing. That's good thinking. I like it. And second factor is that not only these, the molecules don't have only potential energy. They have also kinetic energy. That is proportional to temperature. Okay. If the kinetic energy is proportional to temperature, and what is conserved for these particles is total energy, then you see that if some particle have small, very low potential energy, it must have high kinetic energy, and opposite. So it means that this particle having very high kinetic energy, this one have very high kinetic energy, means that the potential energy would be rather low. And that makes sense. It's very far away. Instead of being here on the potential energy surface, it's somewhere here. But that gives us an idea that kinetic energy can be controlled by temperature. So in the high temperature, this one would be too small to keep the molecules together. So in the high temperature, everything is gas. In the low temperature, this is enough to get everything solid. Is it true? Turns out that more or less it is true. We define something what is called phase diagram. And phase diagram is a plot that on one axis you put temperature. On other axis you put pressure. Now I tell you how to define phase diagrams. So as I said, you always start by putting on one axis pressure. And the other axis has temperature. Now, everything starts at the place where pressure is 0 and temperature is 0. Now, every plot of this type has something what is called triple point, and we'll define it in a moment. From the triple point, there are three curves going out. One curve is going down there, one is going up, and one is more or less going like that up. Now, in this region, you have gas. In this region, you have liquid. In this region, you have solid. What does it mean? If I go with temperature to higher and higher temperature, I'm moving from solid, liquid to gas. Normal. First I have melting, then I have vaporization. What happens when I make the pressure higher and higher? When I make the pressure higher and higher, I'm coming from gas to liquid and then to solid. So there are two ways of making a gas solid. First way is get with the temperature lower. Second way is just push them together, which makes sense. If you have atoms being in the gas and you push them together, finally they come close to each other. They make liquid when they are still moving next to each other, and they make solid when they only move like that. Now what these special curves means? First let's start with this one. This is called phase border. And in fact, this one is also called phase border. And what it means? It means that if you put temperature to T1 and if you put pressure to P1, at the same time, in the same box, you have liquid and gas. They don't want to become liquid, they don't want to become gas, they are just at the same time. This is difficult to imagine, but probably much easier for you would be to imagine this situation. If the T2 and P2 imagine a lake in winter that is frozen, and now the spring is coming. The temperature is 0 degrees and the pressure is around 1 atmosphere. It means that on the surface of the lake there is a lot of pieces of ice. They are flowing. It can last like that for weeks. The temperature is 0, but the lake temperature is not changing. There is still a lot of ice floating on the surface. This is exactly this point when we have coexistence of solid and liquid in the same box. I guess this is not a typical view in Taiwan, but you can imagine this in using your refrigerator, for example. Good. So now we defined 3 types of processes. When you change phase from liquid to gas, there would be vaporization. And from gas to liquid, it's called condensation. They are new words, you should remember them. They are coming there and there. From solid, when you come to liquid, you have melting. And from liquid to solid, just freezing. And these are strangers. If you come from solid to gas, you have sublimation, and in other direction, you have deposition. I guess nobody has any problems of showing vaporization, condensation, melting, or freezing, but there may be some problems with sublimation and with deposition. Any examples from everyday's life? CO2, good. Do you know this, Baskins and Robbins? They are selling ice cream. I'm not sure you have it in Taiwan. Well, they have in many countries in the world, but probably in Taiwan you have some other network. Here you have the Hlieb and Sol ice cream in many places, right? Okay, anyway, when you buy ice cream in the shop and you want to bring them home, usually they give you a box with the ice cream when the ice cream are inside. And except for this, there is a small box with white thing there. When you come home, it's twice smaller than it was. This is solid CO2. Okay? And why they give solid CO2? Why they don't give you just solid H2O? That would keep the temperature the same. The reason for that is very nice. Turns out that at the normal temp, not normal pressure, 1 atmosphere, water would be somewhere here. So the solid first would become liquid and then would evaporate. But before evaporation, would make your box wet. But for CO2 at normal temperature, we are here. The solid, it's directly becoming gas. It doesn't go to liquid. If our temperature of our life is not 1 atmosphere, but we are here, then they wouldn't give CO2. Okay. So we know the evaporation processes and processes of changing phase. Now, there are two strange points on this plot. One is here, triple point, that I said that we discussed in a moment, and another one is here, which is called critical point. Let's start with triple point. Triple point, when the temperature has some special value and the pressure has some very special value, notice that triple point is only 1. So there is only one value of temperature and one value of pressure. In this case, ice, water, and vapor are coexisting. Since I wrote ice, water, and vapor, I must put here H2O. But of course, every other chemical has their own triple point temperatures. I don't remember what it is for water, the triple point. Let me check this. Is some very low pressure, if I remember correctly. Freezing and melting, chemical, water, okay. They give the temperature. So the temperature is very close to 0 Celsius. And pressure is very low, but I cannot tell you now what pressure it is. Probably around 51 over 50, 50 of the atmosphere. But I have to check this, sorry, I didn't prepare. So we have the triple point having a special conditions for pressure and special conditions for temperature where all of them are together. Sounds strange, but when you think longer, why not? We have water and ice at the same time. We have solid and vapor at the same time. At boiling pot, we have at the same time gas and liquid. Why not together? Sounds strange, but maybe. And the reason why it's not normal for you, because you see there are many conditions, many different conditions when two phases are coexisting at different temperatures, different pressures, so you meet it very often. But this one is only one single setting. You don't meet often. I would say you never meet. It's a measure 0 set. Okay, let's go further. No, critical point. Yeah, critical point is something strange. And to explain what is the critical point, we should understand what is really the difference between the gas and the liquid. In the gas box, two particles are moving randomly. Well, not two particles, many particles are moving randomly. In the liquid, similar thing happens. Particles are moving randomly, but now there are many of them. So they are all the time hitting each other, changing energy all the time. But generally the difference between them is very small. We will define it a bit later, not today. What is really the difference between gas, liquid and solids, because it's important for our understanding. But today we just should remember that here the distance between particles is much smaller than the distance here. So when you start changing pressure to higher, 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 turns out that you squeeze the gas particles to such a small volume that they start looking like a liquid. And turns out that if you go with your temperature to such high temperature and you start doing this here and you go up, you don't notice this border. You make the pressure higher, 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 but nothing is really changing. You are crossing this border, but you don't know it. That's people are saying that this phase and this phase start looking the same at the higher temperature. That's why it doesn't make sense to give any more border between them. What happens if you start changing pressure here? You have gas, 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 and here it starts to be liquid. But here, the gas and liquid are so similar to each other that you don't see a difference of this change. Somebody may ask me, how is it possible not to notice any difference? And the answer would be kind of easy one. I write something what is called heating curve. On this plot would be temperature, and on this plot would be the heat. Heating, you know what is heating, right? So heat means amount of energy given by heating to somebody. So when you start heating some object, the temperature goes up. The temperature goes up with heating, temperature goes up. And so what we are doing, we are traveling on this plot, let's say starting from here this direction. We are heating, 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 and now we came to this place. When you come to this place, turns out that you are still heating, but the temperature doesn't change. And you go to some other points and the temperature starts changing again, but at different speed. What happened here? Here you have just a heating of liquid. This thing is the energy needed for changing the liquid to solid, to gas. And here you are just heating the gas. So if you make this plot, it's very easy to see where the border was, where we went through the black line. And you also see that the blue region and the green region have different slope on this heating curve. Okay, but that was in this temperature. Now I'm coming to the temperature that is here. If I go to this temperature, turns out that my curve looks something like that. Of course, it will be higher. I start from the higher one. I come from here. Then I have the change of phase. And then I have the another heating of gas. But now I'm doing in this temperature, very high temperature, high pressure, I mean. So, okay, since I'm changing pressure, then the temperature should be the same. Okay, if the temperature is the same, the curve looks something like that. Now I go to even higher pressure. So I do it here. And turns out when I do it here, the line of heating looks like that. First, this line contracted to a single point. I don't see it anymore. Second, the slope on both sides is the same. So there is no phase transition anymore. So you say if the temperature is higher than this, or the pressure is higher than this, then there is no difference between liquid and gas. And again, difficult to understand. And the reason why difficult to understand is because in everyday life you don't meet this situation. For water, the temperature is something like 700 degrees. And the pressure is, let me check not to lie to you. Critical temperatures and pressures, water. The temperature is 370 degrees, but the pressure is 200 atmosphere. So it means that the pressure is 200 larger than the usual pressure in this room. Good. Okay, now we are prepared to understand the phase diagram for something more complicated. So let's have some small survey of phase diagrams for different chemicals, and let's see how the real one looks like. This is just model. So we have carbon dioxide. And what you see is that you have one region with solid, one region with vapor, and there is no liquid. Well, in fact, there is a liquid, but it's much higher. So you see that the atmospheric temperature of 1 atmosphere, you see only solid and gas of CO2. You never see liquid. To see liquid CO2, you have to go to the pressure at least 5 times higher than here. And you see that in the normal temperature, which is around 20 degrees, you would see liquid. But if you go to temperature higher than 31, you have the critical point. And there would be no difference between liquid and gas. They would behave the same. Let's go further. This is phase diagram of carbon. Somebody may say, strange, carbon? Carbon is never gas. It's never liquid. No, it is. It's just very unusual temperatures and very unusual pressures. So you see that carbon is a gas in the temperature higher than 4000 Kelvin. Wow, we hardly ever have such high temperature, but be very careful with your pencils and with your jewelry in say high temperature because they may evaporate. Moreover, carbon is sometimes a liquid. But not only the temperature has to be high, because in our, this is gigapascal. In our temperature is the usually 10 to the power 5th, right? Hectopascal, megapascal, that would be 10 to the power 9, 8, 7, 6. Our room temperature would be somewhere here. So definitely we would see only graphite and gas when we rise the temperature. Then we have to press the carbon together, make the pressure really high to see something else. So liquid one starts at the pressures 100 times larger than our usual pressure and very high temperature, of course. That's why we never really see this liquid. But now we have something interesting. We have two different solids. One is graphite and one is diamond. You know very well that carbon has two different solids. Now you know the nanotubes and fullerenes that he has more than two solids. But they are not on this plot. Maybe somebody will make the plot one day. So the first thing you see that the diamond exists only if the pressure is very high. Temperature doesn't matter. It exists in all the range of temperatures, but the pressure must be very high. But then you say, no, something is wrong with the phase diagrams. Everybody's seen, at least on TV, the diamond at least once in their life. So what is wrong with the phase diagrams? Because the phase diagrams shows an equilibrium situation. It shows the situation after all the chemical and physical reactions finished. They went to the steady state. So it means that in the low temperature, all the diamond is all the time changing to graphite. But very, very, very slowly. Maybe you need 1 million or 2 million years for the diamond to become graphite. And for me, I never seen really such a change, but turns out that if you put your diamond to the box with higher temperature, then this change is very fast. You are lucky, I missed. Okay, now what are the regions with the dots, with the strokes? It means in this region, if you are changing the pressure very slowly, the diamond doesn't become graphite. And if you are rising the pressure very slowly, the graphite doesn't become diamond. But if you cross this line, then the change is very sudden. Similar thing happens here. If you have the vapor and you make the pressure very slowly, larger and larger, it doesn't become liquid, it's still gas. But then when you shake, it just liquefies in one step, very fast. So when I was a kid and the winters were very cold, now somehow they are not so cold. I was collecting books on chemistry, very small books with how to blow up your house titles. And one of the things that was written there was, take a probe, put inside the crystals of Na2S2O3. This is thiosulfate, and this more or less looks like that. In reality, it's a crystal, so it looks a bit different, but that's more or less you know how it looks like. Take this thing. This thing is maybe look unusual, but it's used in photography to develop photos. So it's very easy to buy it in a shop with Photoshop. So take this thing, put inside, and melt it. Okay? After it's melting, it's becoming liquid. Then put it in a very quiet place and let the temperature very slowly go down. So the liquid should become solid again. But because this thing, this thiosulfate, has this type of regions, it's still becoming a liquid. Even in this region, in the solid region. So later when it was staying in some cold place and you are going out and you are cold, you just grab 2 probes in each pocket and you shake them. Then becomes from liquid they become solid very suddenly and emit a lot of heat, the heat of change of phase. And you just have some heater with you all the time. I guess it's not very useful in Taiwan, but I'm coming from cold countries. So. Okay, let's continue. So these regions, they can be used for strange purposes. Let's go further. This is the phase diagram of water. There are 2 strange things here. That's the triple point. So you see that the pressure must be 4.6, but torr. Torr is some strange unit of pressure coming from the name of Torricelli, the Italian physicist. What computer game was it last night? So we have this strange unit of torr, and 760 torr is 1 atmosphere. And you see the triple point is just above 0 and very, very low pressures. Good. And, well, everybody may think that this is the phase diagram of water, but the truth is a bit more complicated. Yes, it's true it's only 1 vapor. Yeah, it's true it's only 1 liquid. But with solids, it's similar situation like with carbon. You have more solids. And here you have the situation, the real phase diagram, scientific phase diagram of water. You have the vapor, you have the liquid. This part we know. There is a critical point when the vapor and the liquid, there is no difference between them, and you see the temperature is in Kelvin. So the book was giving in Celsius. So I was right, around 700 Kelvin. Okay, this region we know, but what happens here? You see a very strange, everything is blue, there are black lines of phase diagrams, and first thing we should see is that the pressure in pascals is very high. Our room temp pressure is here. We are on this line. So in this room temperature, I can see there is 1C, 1H, and 11. What does it mean 11? What is 1C? What is 1H? What is 2, 3, 4, 5, 6? All these numbers. These are different types of ice. And I will show you in a moment some of them, that you have just idea what does it mean different types of ice. And as you see, this region can be magnified, and you have here, you have a 5, 3, 2, 1H. This is pretty complicated. It takes people a lot of time, a lot of money to find it. Why people would do it? To understand science. In the case of water, it's not so important to know how many types of ice we have. But it is important because ice is one of the most important things in the universe. The temperature is very low and we have a lot of water. Usually it's in ice form. So understanding the ice, you can understand some comets. I mean, comets are in large amount of made of ice. So let's see different types of water now. You have here the ice 1C, the most popular one. And you see that every hydrogen is pointing to the next oxygen, making a very nice network of hydrogen bonds. But even notice that in this ice you have very large disorder. When I say disorder, I mean that this molecule can flip the hydrogen bond here. When this is flipped here, this hydrogen must be flipped somewhere, another hydrogen must be flipped somewhere, and finally it closes. So you can change the path of closing hydrogen bonds to get different molecule, but still the oxygen molecules would be in the same positions. This is called structural disorder, and we have some non-vanishing entropy at 0 temperature coming from this fact. But we will discuss it a bit later. Then you have some other types of ice. Ice 8, when you see that the waters make something really strange, tung, tung, and here they are in the plane. Ice 2 and ice 3, when here you have the hexagonal rings of waters. 6 of them, and again 6 of them. And here I don't even want to analyze this one. I don't understand these forms. But different arrangement of these water molecules in crystal can give you different properties, and not only properties, as we've seen on this one, when you change the pressure from here to here, you would see also a phase transition. It means the heating curve would have a flat region here. Good. What more we have for today? Sulfur. Sulfur is strange. Because sulfur has like 2 liquid phases. Liquid and monoclinic is this kind of liquid. In one case there is the SH, S8 of them making rings and flowing together. This is not really solid. So we've seen some model for phase diagram, but now when we come to some other things, we see that this model is very often changed to something more complicated. This is the phase diagram of helium. And helium is very strange. It's very strange. Because first, you have gas, helium, only in the temperature lower than 5 Kelvin. If you go to temperature higher than 5 Kelvin, there is no difference between gas and liquid. This is the first thing. Second thing, there are 2 different liquids of helium. And there is also solid, which hardly anything is known about solid. But we have the 2 different liquids. Anybody heard about the superfluid helium? Yeah. This is a strange thing. When we have a box and we put a liquid inside, the liquid stays there, but not superfluid helium. What superfluid helium does, it starts climbing the wall on both sides, and finally it goes out. So after some time, it didn't evaporate, but all the liquid is around and nothing is inside. What happens? Why? Turns out that superfluid helium doesn't like interaction with each other, but it likes interaction with everything around. So it's trying to make the surface of interaction as large as possible. So get out. First, at the beginning, starts to interact with the glass, and then making the surface larger and larger. It has to go against gravitation, but still the energy of interaction is higher than the lost energy of gravitation. And finally it gets out, then it's easy part. So you should remember about the superfluid helium. I have few more. Yeah, let's finish these few pictures more and then let's make a break. This is iron. And as you see from this picture, not much is known about iron. This is a very dirty one and very disorganized. But look at some other part here. This point was published in Science, 95, 12 years ago. This one, this line was published in Science, 97. This is in Nature, 93. It means that people finding these things It's extremely difficult, and if somebody finds, you can publish in the best journals in the race, physical review letters. I don't know what is this one. And this one is a bit different because they, instead of putting temperature here, they put it on this axis and pressure is here, but it doesn't make big difference. So if you switch them, you would have the solid here and you would have the liquid here. So this is for ion. When you mix two things together, things are becoming extremely complicated. Here, we are mixing copper, you see, copper and aluminum. When you have only aluminum, then it's kind of easy. You have solid, you have liquid. When you have only copper, it's easy. You have solid, you have liquid. Now, when you mix two liquids, turns out it's the same liquid. So there is no phase transition between the liquids if you change from copper to aluminum. But if you have the solids, wow, there are really many phases. 1, 2, 3, 4, 5. I don't want to count it, but more than 30, I think. Different solids, different crystals made out of aluminum and copper, depending on temperature and depending on the concentration. As you see, there is no pressure here. If you put pressure, that would be much more complicated. You can do something strange, like you can measure the chocolate and vanilla mixing. I don't know why this is important, but people are doing such things. And you see that if you have the percentage of chocolate, if it goes too high, you have the solid chocolate, and then the chocolate melts. Well, I don't want to analyze this. I don't understand this. What is what? No, I don't know. Maybe this is ripple. Small pieces of chocolate floating. But I don't know. Well, but the point in showing this one is that people are doing strange things for money. And I believe some chocolate factory ordered this thing. Okay, you can go farther. You can mix 3 things together. But if you mix 3 things together, there is no place for temperature or pressure anymore. We have just the concentration of nickel, chromium, and iron. And you see that in this concentration, you still have a lot of different crystals. You have steel, but then you have some strange different things. And maybe that's the last one. So, from the next class, we are going to discuss these elements. We are not going to take care of the chemical system, of the chemical interactions between them. We already know that most of them are closed shell and they don't react. And this one make different connections, making different gases. So we are going just to analyze the particles of gas in in the large amount, many of them together, to understand how the general gas is behaving. And that's maybe a good moment to finish this class. Thank you.